Next up is David Leitner. David is going to talk to us about the art of architecting for scale. You're going to give him a lovely, warm post-lunch round of applause as he walks on, which he's doing now. He's going to make his way to the lectern. I'm going to walk off stage. Enjoy, David.
So you can hear me, I assume. Sounds good. Feels really good to be back at Craft. Amazing, as usual. Great to be here with you. And I'm very excited to what I'm talking about today. So those people who hear talks about me in the past usually know that I'm talking about some architectural things. And to be very honest, when we aligned in December that I will do a talk at Craft, I wasn't 100% sure what I will talk about. So I usually come up with this, fancy talk titles like The Art of Architecting for Scale. And just now in the speaker lounge, somebody asked me, hey David, what will you talk about? Will you talk about pictures of architecture, right? Will you talk about some kind of Miro diagrams? That's not my purpose. That's not what I'm here for. What I would like to talk, as I usually talk about, is how we can shape architectures in a way to allow our organizations to scale. And when you take a look at the schedule here at the Craft Conference, there's a lot of great content on autonomous teams, on improving the flow of value, on building platforms, and all these things which basically should allow organizations to deliver features faster and better. But I sometimes have the feeling that we miss, the technical foundation, the stuff we basically need in the first place that we can apply all these concepts. And this technical foundation usually needs to be scaled, and as you will surprisingly realize during this talk, needs to be more chaotic than most of you probably think. So how many of you are working in distributed systems? Cool, that's nice. And how many of you are working in a distributed system which probably costs thousands of dollars or millions of dollars if it goes down? Okay, still a good amount of people. And how many of you will during this talk at least once take a look at some kind of ChatOps Slack channel to figure out if the system is currently up and running and healthy? Yeah, me either probably. Okay, so we will focus especially on those topics. And before we start, you probably ask yourself, who the fuck is he and why should we actually take care of what he has to say? And we on record, I just see, so maybe we can peep the fuck word out. I said it now 2 times. But I'm David. For those who don't know me, I'm a principal engineer for a company called SQUER Solutions. We have branches in Munich and Vienna, and what we usually do is we help organizations in building great digital products. And my take on this is usually to help customers to get their systems right, to optimize the flow of value to their customers, right? I do a lot of workshops, I teach at university, and always this focus on distributed systems and how we can build them, that they allow our teams, our engineering teams, to deliver fast-paced value in a world where everything seems to change. Customers seems to change, organizations seem to change, requirements seems to change. And when we take a look at software in general, when we start to understand why are we such in a huge demand on this topic, on how we can deliver fast flow of value, then we always end up with some picture like this or similar, right? The more people we put in organizations, the slower it usually feels in the way how we deliver features. And I was myself a co-founder of a startup, and if you ever talk to an engineer who was an early kind of engineer in one of the startups, then he will usually tell you the same thing. He will tell you the thing that, it feels like we were faster in delivering features when we were 5 people than we are now when we are 120 people. So on the one hand, it seems that we deliver less features. On the other hand, it seems that we get a lot of more failures, that we get a lot of more outages, that we get less availabilities, that we need to deal with a lot of more bugs, the bigger our engineering organization is growing. And this is usually when we talk about complex systems, right? When we say, I'm working in a complex system, I don't say I'm working in a system where we didn't deliver a feature for the last 2 months, right? Doesn't sound cool. I say I work in a complex system, right? And I also don't say I work in a system which goes down every 2 weeks, but I work in a complex system. And this goes actually completely against the goal to optimize the flow of value to our customers, or then North seems to say it in a much nicer way, to safely and sustainably reduce the lead time to thank you. And if we think about this, if we start the story in the very first beginning, when a startup founder or when you as a product team start to build a feature, then you usually have some kind of request. You have some kind of idea, you have some kind of customer value which you want to deliver. And you probably start with a very simple and small system, right? Something that brings value, something that solves the problem. And when this small thing has an issue, it's probably quite easy to figure out what is the cause of this effect. What is the cause of this issue? Because we can just trace back, go back into the debug tracer, or can check the stack traces and figure out, okay, this seems to be the problem, we can easily solve it and we can quickly fix it, right? And as the system usually grows over time, as all our systems grow over time, it becomes from a simple system probably to a complicated system. So the relation between cause and effect is still given. Also, it's more complicated to figure it out, it's still there. We can still understand, okay, this fire is caused by this bug here, right? And the bigger our systems get, the more complicated they get. At some point in time, we will figure out, okay, we just woke up with another monolith, and we need to modularize this thing, right? That's the classical journey which we usually go through. And modernization is very important and very good. We need to kind of, do all the things which we learned over decades now, information hiding, creating well-structured contracts between our modules. But I think here something went totally wrong somewhere in the last years. Because when we talk about modularization, and when I hear people saying we need to modularize our system, what they usually mean is that we need to kind of slice this shit up into small distributed systems, right? Maybe we can peep this out again. But that's exactly the point, that there's this common misunderstanding that people mix up distribution and modularization. And these are two total different things. You can have a well and a bad modularized system, right? And you can have monolithic deployment units or distributed deployment units. But if you have bad modularization in a monolithic deployment unit, then it's probably not the problem of the monolithic deployment unit that you end up in a big ball of mud, but it's a problem of modularization. And I'm fully with Joseph Joda here, who coined the term of big ball of mud, who says that SETI architecture has been undervalued for so long time that engineers regard life as a big ball of mud as normal. And I think this brings us back to this misunderstanding that we say, when we have bad modularization, we need to shift into distribution. And where we usually end up, we all know, is a distributed monolith. All through, I think the term distributed monolith is quite bad, because it indicates that the monolith is something bad, which is not the case, right? We should call it distributed big ball of mud or something like this. So if we want to go for modularization, a much healthier and more valuable approach is to probably go into something which we tend to call a well-structured monolith these days. So there are multiple good reasons to go for distributed systems, don't get me wrong, but modularization is probably none of them. So if modularization is not a reason to go into distributed systems, why do we all go into distributed systems then, right? I even said in the intro that I'm kind of fanatic about distributed systems and that I work for distributed systems in my entire engineering life, I could say. So what are the reasons that we go for distributed systems? Well, basically, I usually see two of them. The first one is a technical one, right? We want to have the benefit of independent scalability. We probably have the circumstance that some parts of our systems need to scale much higher than other parts of our systems. One part of our system can have 10x traffic and another just stays, solid, stable as before in terms of traffic. The probably second technical reason is that we want to have this technology agnosticness, right? That we say, you know, we usually build our services in Go, but we have this one service which takes care of machine learning, so probably write it in Python. So this is the first family of reasons, those technical reasons why we go for distribution in our deployment units. But usually these are not the driving factors, right? When I work with clients, with customers, then in 90% of the reasons, that's not the main reason why we go distribution. The main reason why we go for distribution is the benefit of ownership, right? We want to make teams able to take ownership of their subsystem, of their service, to take ownership, to take responsibility, and to also be accountable. And to actually also take the consequences. So they build it, they own it, in the best case, they build it and even run it, right? And that's a criteria for distribution, because you cannot achieve this in a single deployment unit. If I would be an engineer in module A and work on this, single deployment unit where 3 other teams are working, I could not take responsibility for my module that it will work safely, because maybe somebody in module B, has an issue, and this issue is usually sprawling across the whole deployment unit and brings the whole monolith down. So I, as engineer in module A, will never take responsibility for my module to ensure and to be accountable for its being healthiness and its being working. So this is why we usually go into distributed systems, to take ownership and give ownership and responsibility to the teams. And this is basically, from my understanding, the idea, or has always been the idea, that we kind of, slice these big teams up into smaller independent teams that then basically, can drive the value to the customers by having ownership of a clearly defined subsystem. And this is probably the best reason why we want to go into distributed systems by autonomous service-based architectures. And now comes the gotcha. Now comes the important part. When we move on this matrix from the left side to the right-hand side, then we move from complicated monolithical systems to complex distributed systems. And what do I mean by this? If you take a look at this example again, where we have this landing system. So we work a lot with banks, probably a system which tells you if you're allowed to get a loan or if you're not allowed to get a loan. And if the system doesn't return a valid result, returns you're not allowed to get a loan, but actually you should be allowed, then as I said before, we can easily, well, probably not easily, but it's complicated, but we are able to trace back the cause of this effect. Because maybe somewhere the age calculation is messed up and returns a wrong result, and that's why probably this person doesn't get a loan. If we now fix this, everything should go smooth and should work properly well again. If we now walk into the land of distributed systems, and if we have a similar issue, that the person doesn't get a loan because it should get a loan, then probably our end point of analysis is that some other system returns that this person shouldn't get a loan. So what we can do is we can, of course, go to the other team and say, hey, can you please double check this and understand why you return here a wrong result? And this team will probably figure out, okay, we returned a wrong result because we already before got a wrong result, right? And then they need to go to this team and say, hey, why do you return us a wrong result? And they need to do some debugging and figure out, okay, there is some logical error in our system. And this simplified example, of course, shows that in a complicated monolithical system, we usually have a clear relation between cause and effect. It's usually given. In a complex distributed systems, it's usually not given. And that makes a huge difference. And what you then usually realize very quickly, sorry, the clicker seems to not work properly. Yeah, what you then usually realize very quickly, that in such systems, our problem is not reliability. Our problem is not that 4 plus 4 returns 10 instead of 8, right? Our problem in most cases is availability, that we were not able to reach another subsystem that probably the network didn't work, probably the other system is not properly configured, probably it returns out back a 500, probably we have kind of a split brain scenario, whatever we have. We usually come from reliability issues to availability issues. And I usually describe this in my workshops by asking the people, what's the difference between a method call within a single deployment unit, so module A calling module B on some kind of instance and doing some creation of a users, versus a method call across the network, where one service goes over the network and calls another service, probably the same functionality. Well, the answer is relatively short. What's the difference between those? Basically everything, right? Beside the fact that both of them want to create a user, everything in between is totally different. And I usually refer them to the fallacies of distributed systems, coined by Peter Deutsch in 1994 already. And actually all of them are still relevant and still true because the fundamental constraints that networks have didn't change since then properly, right? Systems are still unreliable. Latency is still not zero, for example, and bandwidth is still not infinite, right? So we have these huge fallacies of distributed systems in terms of network issues, but not only network issues, right? We can have all sorts of availability issues. As I said before, maybe a service is not properly configured, is not properly deployed, all those things, right? And the point is, when we move from the left-hand side to the right-hand side, the cause of our failures usually moves from reliability to availability. And that's a big thing, because we, as a software engineering community or industry, are very good in dealing with reliability issues. You know, we write tests, we have whole test suites, which usually can help us tackling the problem of reliability. We can ensure that 2 + 2 is 4 and not 6 by writing proper tests for these scenarios, right? But as we move from complicated monolithic systems to complex distributed systems, the cause of our failures usually moves from reliability to availability. Of course, we can still have reliability issues, but our main issue in these systems is availability. So all through, we theoretically allow, by this, kind of slicing into smaller services, the teams to independently deliver value. We usually see something different. We usually see a system that has huge issues with outages and huge issues with availability, and maybe at some point in time, so huge issues that the teams are not able to do anything anymore besides, fixing issues. And the root cause of this is that, in my opinion, but I'm happy to discuss this afterwards, most of the teams I'm at least working with didn't fully get the shift. They treat complex distributed systems the same way as they treat complicated monolithic systems. And what do I mean by this? A good example is usually when I go into teams and I ask them, let's take an online shopping system example here, and ask them, hey, what's going on? And they say, yeah, we have an issue here, and something is not working as expected. And then we figured out that the response is not working as expected, or is not as we expect it should be, right? And what they then usually do is they take the classes and go through the whole system to figure basically out what's going on, where's the issue. And at some point in time, they will probably find it. 2 weeks later, they find, okay, the warehouse team has a bug, that's why our system is not working properly. And this is highly inefficient, of course, because, as I mentioned before, the relation between cause and effect is very complex to figure out, first of all. And also, they would kind of bother them to fix the issue, which they, of course, should. They will not get finished with this, because there will be another issue, and there will be a broken database, and there will be a failing network connection, and there will be a misconfigured service, all these things. And if you just jump through the system to fix all these things, then you're following the wrong mindset, the wrong understanding of how we need to build systems in a complex distributed system. Because what we do here, and what many teams I'm working with are striving for, is a stable production environment, which is totally elusive if we're working in a complex environment. And sometimes even a chaotic environment. And the sooner we realize this, the better it probably is, because what we need is, we need to architect for failure in mind. And give me another example. Online shopping system again. We have the payment service team. Payment service team shouting, saying, hey, we are pissed. Our system is still, or is again not working because the account service team messed up something in their system and we are not able to fetch users, right? And if they come to me with this request, I ask them, hey, are you sure? You know, doing a payment is probably the most important feature of an online shopping system, right? If you cannot do a payment, you cannot buy anything. If you cannot buy anything, you will probably not use the system and go to another system where you can shop your stuff. So the first question should be, is it really true that you think that your system is down, is someone else's failure? Right? Probably we should increase the resilience first of all. Probably we should not go fully down if we cannot fetch users. Probably we should return a failure and say, you know, we are not able to do payment now because we cannot fetch users, which is probably still a very, very bad option. Because as I said, doing a payment is probably the most important thing for this business. So maybe we can improve the resilience even further and can say, I don't know, introduce a cache. So that when we have the user in cache already, we don't care if we cannot fetch the user. But of course, then we have cache misses, and maybe we can even elaborate closer on this solution and say, we have anyway kind of a streamed architecture here, and we basically have a stream which gives us all the user changed events and basically build up a projection based on those user changed events. And then we're in the lucky situation that we have all the users in the shape how we need it as an account, as a payment team, available. Doesn't matter what happens to the account service. Can fully blow up, and we basically can do a payment. And this is what I mean when I say architecting for chaos and failure. Because those things will happen. It's just a matter of time when they will happen. And of course, we also need to shift this on the other side of the things. We also need to be aware that everybody who calls us will probably call us in a strange manner at some point in time. Maybe we have 10x traffic at some point in time, and we heavily need to scale. So we need to keep these mechanics in our system for scalability. We need load balancers and circuit breakers or waiting rooms, whatever we need. We need something which secures us from the outside, so to say. And basically, probably some caching that we can fall back to a cache if our system is overloaded and things like this. And that's exactly the point. We need to architect for failure and scale in mind. Because the most important sentence on this slide is probably that services that can run in chaotic environments can run everywhere. But services that only can run in stable environments can only run there, right? And if this journey continues, then the payment team comes to me again and says, we are again pissed because we cannot execute a payment. We're not able to execute a payment because the payment gateway team messed something up. And then the first question should be, why actually? Why do you as a payment team, who is responsible for executing payments in this company, have a liability on another team to fully fulfill this customer journey? Why did we slice it like this? Shouldn't it be like this, that you kind of have this end-to-end customer journey in your ownership? That you as a payment team take care of, the button click on doing a payment till the request against the external payment gateway. And I fully get this point, and usually we say, yeah, too much cognitive load, and that's a more than valid argument, of course. But still, it shows that we probably sliced incorrectly, because we could also decrease the cognitive load by saying we slice in a way that we have a team which does SEPA payments and we have a team which does credit card payments, right? And this allows those teams to stay within their complicated module boundary or their complicated process boundary, right? And that's a big advantage to kind of stay in your control area than in comparison to spawning up this process over multiple teams, which make it automatically to a more complex process in comparison to a complicated process we had before. So what we also want to do is we want to architect for end-to-end customer journeys. And we, as working on architecture, we as teams driving architecture, we need to take this serious, right? That's probably most of the most important ingredients for successfully distributed systems if we get this end-to-end journey slicing correctly. And of course, I fully get the point that we have complicated subsystems, or however we tend to call them. We have those core teams who take responsibility of a very complex domain, which will blow up the cognitive load of a streamlined team. And where we say, hey, fraud detection is something so complex, we need to shift it out of the payment teams and say, hey, you take care of fraud detection. But then we, as a SAPER payment team, need to understand, how does the system actually react? What's the capabilities of the systems? What's the availability of the system? I really still wonder how seldom we find availability metrics in distributed systems. How less often we can understand which availability do those endpoints have. How many nines do we have, right? Do we have nines at all? Probably we don't know. But if we have nines, this is an important ingredient for our architecture, because we need to understand if we have 3 nines, we have a downtime of 8 hours a year, right? And when we know this, oh, that's an important remark. Also, also a planned outage is an outage, right? Because I often hear people saying, hey, our system has 4 nines, but every 2 weeks, we have a maintenance windows of 2 hours, right? So the general availability of a system. But if we know this, we can basically architect our system in a way to utilize this information. And also in my workshops, I often also ask these questions. Can our service have 4-9 availability if our dependencies just have 3-9 availability? Who says yes? Who says no? Of course we can. That's the whole point, right? We can introduce this REST scheduler in our system if we know we have 3-9 availability, and ensure that whenever we cannot execute a fraud check right now, we will put it into some kind of waiting list, and we'll do it later on, and we'll let the customer know, hey, it currently takes longer to do a fraud check, but we are still available for our customers, right? And when we maybe have 5 nines in this fraud check system, we don't really need to care, right? Because these are 5 minutes a year, right? This is half a minute, not even in a month. So in this case, we probably just return an error and say, hey, retry it again. The point is we need to know this. We just can properly architect if we have this information about the availability of our subsystems. And the same thing then goes true for all the other metrics which are usually important in the architectural context, like the mean time of failure, and so on and so forth. And for me, the same thing goes true for platform teams, right? I don't care if a team manages its own infrastructure or takes an infrastructure from a platform team. It's the team's responsibility that they need to deliver their business value. If they are faster in doing so by having their own Kubernetes cluster, which they need to update all 3 months, or if they utilize an existing Kubernetes cluster from a platform team, I don't have a strong opinion on it. I just say that they should be able to decide on their own what they do. And to be able to decide on their own, the platform team needs to provide proper SLAs. They need to give them information. Hey, what are we guaranteeing you, right? And if these SLAs are just 2 nines, and the team says we need 4-9 to fulfill our business need, then they have an answer if they can use the platform or not, right? So we need to architect based on availability. A very important other property if we architect for scale. And what we usually also often see, I just tell you some random stories from my work life, by the way. What we usually also often see is that we as teams need to deal with legacy systems. And legacy systems are usually bad, and they are mainly bad because they don't have clear ownership. Nobody takes care of them anymore. Nobody takes care that they are running properly, that they are maintained properly, just some random people adding some features from time to time because they need them there. But nobody really takes care that this legacy system is up and running, is health, is scalable, is scalable. And this is where we usually need to take ownership. This is where we usually need to carve out things of the monolith and need to put them into our team, right? And what we need to do, of course, is we need to extract away the logic into our new service, and the more harder part is we need to extract away the data into our new database. Right? And the problem with those legacy systems is that they have a lot of readers and writers, some maybe on an application level, some maybe directly against the database. And what we then usually do is good old strangle fig. We introduce an API, and once this API is ready, we shift over all the data. And all the writers and readers will have a short downtime because shifting over all the data takes a few minutes or seconds. And once everything is shifted over, we tell them, okay, now redeploy and go against the new API. And also this is already a mess because we have some downtime. It's also a mess because what's happening if the API server doesn't work as expected and we need to shift back? These are the situations that give me a heart attack, honestly speaking. And we should know better, because we can solve this problem in a much easier and smoother way, that not everybody is afraid of monolithic decomposition. We can just build up this new service, build an API as we did before, and do some proper change data capture, for example, to ensure that data on the old side is also available on the new side. So we can at least already move over readers. And if we want to do it fully properly, we can do this in the other direction, this loop. Whenever somebody writes on the new system, we send an event which we store in the legacy database. We of course need the application, otherwise we end up in endless loops. But in theory, we can now move over the writers. And if this writer fails because it cannot deal with the new API or something has changed, and we need to deploy an old version which goes against the old monolithic legacy system again, then this is just working, right? And this is how I want to have my migrations. I fix the writer and migrate it again over to the new API. So we need to architect with a non-negotiable zero downtime mindset. It's so important. We don't want to allow any zero downtime in our way how we kind of manage migrations, for example. We can do better, and we will on the long run see that this makes things much easier for us, because we can evolutionarily shift over old systems to new systems and vice versa. And last but not least, we need to start dancing with the beast, I would say. So who of you who's working in distributed systems has a disaster recovery plan? Can you please raise your hands? Quite a few. Who of you has trust in this disaster recovery plan? 2 hands, I think. That's amazing. That's usually the ratio we get here, right? And that's exactly the point. I don't like disaster recovery plans, but I think we should be prepared for disaster. And I think a much better way to prepare for disasters is kind of a game day. It's kind of a game day where we sit together on Tuesday at 2 o'clock in the afternoon and shut down this database. And I like to do this planned on Tuesday at 2 o'clock in the afternoon, more than unplanned on Saturday at 2 o'clock a.m. when one crooked developer needs to get up and needs to fix the stuff. I want to do it in a setting where we know that we will have this problem and we need to deal with this problem. And I want my production not always to be smooth. I know there are different opinions on doing game days just on staging or doing game days on production. I'm a big fan to do them on production because I don't want my production always to be smooth. I want it sometimes to be very chaotic as possible, actually. that as many things could go wrong that will anyway go wrong, so that we can build up the right processes, that we can build up the right response for this, that we can build up self-healingness and self-recovery in our system, that when it will hit us unexpected, we are prepared. And I can tell you a story, a disaster recovery plan. It's roughly 3.5 years ago. I helped in an organization building up an application platform. And we did it really the well way. Everything infrastructure as a code. So 0-day deployments were infrastructure as a code. So basically we spin up Kubernetes cluster. This Kubernetes cluster spinned up an Argo CD. This Argo CD took all the services and deployed it, right? So if our full cluster would go down, we would probably have a completely new environment with all services up and running, with backups included in 25 to 30 minutes, I would say. And then we were sitting together and playing this tabletop disaster recovery game, right? And somebody said, what happens actually when our GitLab goes down? And somebody says, that's not a big deal. We have this 0-day deployment Argo CD, it will just spin up a new GitLab instance, right? And then somebody said, but where does it get the infrastructure as a code? Because the infrastructure as a code lives in GitLab, right? And that's exactly the things you figure out on a game day. That's not the things which you figure out by, sitting together in a meeting at 5 p.m. where everybody wants to go home to consider what should we do in case of a disaster, right? And we can do this game days every week. We can say the network outage. We can say we game on a service which is wrongly configured. Because we need to embrace chaos in our architecture. That's the whole point of shifting from complicated monolithical systems to complex distributed systems. So I gave you a couple of insights into things that are important in architecting for scale, and let's quickly sum up to also have some time for questions. So we started, and this was kind of a personal favor for me, to clarify that modernization is not a reason to go for distribution, right? And the second thing we kind of discovered is that once we move from a monolithical deployment to a distributed deployment unit, we go from complicated to complex systems. And this is an effect on how we need to architect our systems. And I showed you 5 things which we need to probably take care of in terms of we need to architect for failure and scale in mind. We need to architect for end-to-end customer journeys. We need our architecture to be driven by given availability. We need a non-negotiable zero downtime mindset. And last but not least, we need to embrace chaos because we cannot avoid it. And if you follow those 5 points, chances are a little bit higher that you not end up there, but you end up with teams that keep the floor value high and keep the amount of outages low. Or to phrase it in different words, keep the lead time to thank you low even at scale. Thank you a lot. This was Architecting for Scale. I hope this was useful.
Thank you, David. We have time for questions. We have 5 minutes for questions. That's for you.
Oh, thanks.
I'm going to read them. You're going to answer them, okay?
That's me. Nice.
Okay, Roland. Roland Papti says, if you slice the payment module E to E, who is responsible for the code duplicates that arise? Who, David, who?
Well, I mean, who should be responsible for the code duplication? Code duplication usually is duplication because it lives in 2 teams, right? So I would say both teams are responsible for deciding if in this situation they should duplicate the code or in this situation they should rather go into dependency, right? This is not a black or white decision, unfortunately. Hopefully I didn't say with my slice that you should, duplicate everything to have end-to-end slice. But of course, in distributed systems, and I guess we kind of align on this, is that duplication is usually not such a huge problem or is not treated that of a huge problem anymore than in comparison to, I would say, classical monolithical applications. And one more sentence on this maybe, I think we also need to differentiate, is it application, is it real application, or is it just at this certain amount of, or at this certain point in time, the same thing, doing the same thing, right? Because then the chances are high that things will evolve differently over time, and that it's just, time-limited duplication, which is usually even an advantage then in comparison to, slice it out into a reusable service or stuff like this.
Thank you. Anonymous asks, starting with the big mud, would you start one by one, or would you first plan out the desired architecture first? Mud has architecture?
Yeah, that's a very good question. I think I have this someone explained already. Let me quickly jump back to a slide where I can explain this properly. And the point is...
Can we put David's slides up?
Oh, sorry.
No, it's just a button. They're super good.
The point is that we basically, if you take a look at this matrix, have a few options to get from a big ball of mud to an autonomous service-based architecture. The point is, what we often do is we go from big ball of mud to distributed monolith. And the thing is, we are locked there. I strongly believe that there is no way to get from a distributed monolith to an autonomous service-based architecture. And this is usually where companies end up and say, this didn't work for us, let's shift back to the monolith, right? What's usually the much better approach is to modularize the monolith, to come into a well-structured monolith, and from there on shift into a distributed system. But I also know that this doesn't always work, because sometimes those monoliths are so broken that we cannot, shape them around anymore. So what's then usually better is to go from a big ball of mud to an autonomous service-based architecture. But this is hugely risky because it demands a lot of knowledge within the team. Teams which usually work for decades on monolithic, non-distributed systems usually need a lot of advice and a lot of consultancy to get this right, to get directly from the left bottom to the right top. So I would prefer left up and then to the right. And I strongly believe that top right, bottom right and then top doesn't work at all. Hope this answers the question.
Thank you. Anonymous again. So, would you say that the aim is that domains are self-contained?
Would you say what?
It's gone. It's here. It's the one at the bottom now.
Would you say the aim is that domains are self-contained? There are so many terms in this question which are so unclear, I think, in our industry, that the domain first of all, I don't think that the domain should stay self-contained. I think the bounded context should stay self-contained. And the bounded context is the best case a one-to-one mapping to the domain. So in very short terms, but maybe we can talk at a coffee a little bit longer on what you exactly mean by this. The answer would be yes, yeah.
Okay, last question it looks like. Which open source tool would you recommend for testing reliability of a complex distributed system?
Yeah.
Chaos engineering, e.g. Chaos Monkey?
You cannot really, the point is you cannot really test for availability, right? You can test for reliability, but not for availability. And that's why we use game days and chaos engineering, right? Game day is basically just the concept of chaos engineering. So I would totally go into these directions. I usually have good experience with chaos mesh or, the classical game day where you basically need nothing, then putting some infrastructure down and seeing how your system reacts. So I think the point is not that we don't have proper tooling. I think the point is just that we need to have the awareness that we do it and that we trust in us, that if we don't do it now, we will probably do it in a much worse circumstance somewhere in the future when we don't plan to do it, right? I think that's more the issue we have here, not the missing tools or capabilities.
Okay, that's all the questions, and it's right on time. So thank you very much to David again.
Thanks. Have a great rest of the day.